Hey, it's Ryan. We're going to continue our stellar evolution notes, beginning with low mass stars. We left off in our notes last time defining 3 categories of stars: low, medium, and high mass. We're going to start with low mass. And we're going to note that step 1 through step 6 are done. So we've started in our notes with stellar evolution, or we ended last time on the end of step 6, where we had a star at its middle-aged stable condition where it will spend 90% of its life. And so you may be wondering, how does that star remain stable for so long? So we might ask that question. How can the star remain stable for so long? Remember, that was 90% of its life. And I guess the problem is the gravitational force, the tremendous gravitational forces are trying to compress the core. So there has to be something countering that. Well, keep in mind, in the core of our star, there's the hydrogen fusion, the sort of nuclear process going on. So what I've drawn is 4 consecutive or concentric circles. And actually, I'm going to draw a 5th one, sort of on the outside here. And I'm going to label all of these segments. So this is the chromosphere. And so what I've drawn here is basically like a slice of the inside of a normal low mass star, like our sun, for example. Our sun is considered a low mass star. The inner layer of the under the chromosphere is called the photosphere, and this is the part of the sun that we see the color come from, the photosphere. The photosphere of our sun is approximately 5,400 degrees Celsius. Inside, we have the convective zone. And in the convective zone, I like to draw these convective currents sort of swirling around this zone. This is due to temperature differences from the inner part of the star to the photosphere. The next zone is called the radiative zone. The radiative zone, and so this is where, and we can just label the inner. This is the core, and this is where the hydrogen fusion is undergoing. And if you recall from our discussion of hydrogen fusion, or the proton-proton chain, what we're looking at is hydrogen atoms being, or really hydrogen nuclei being compressed by the forces due to gravity until they create helium and a bunch of excess energy. That excess energy comes in the form of gamma rays, and those gamma rays are making their way out of the convective zone, out of the radiative zone, and into eventually interstellar space, or really, I guess, our solar system space. And so we could note that these represent gamma rays. All the while, we know that there are the gravitational forces from the enormous mass of our star trying to compress the star. And so I'm just drawing the gravitational forces sort of going toward the center, the core of the star. We could note that this is the gravitational force. And so as the core of the star is creating all of this radiative pressure going outward, the mass that creates the star is creating all of this gravitational pressure going inward, and we must create or find some sort of equilibrium between the inward forces and the outward radiative forces. There is one more piece of the sun that we noticed during eclipses, and that is all on the outer layers here. Outside, there's sort of a wide, huge sort of crown that it looks like the sun wears. It's called the corona. The corona, and the corona is actually around 2 million degrees Celsius. So there's a lot of strange temperature changes in and around stars. The inner core is probably closer to 30,000 degrees Celsius. Oh, I'm sorry, that's a lie. The core is 20 million degrees Celsius. We could note that. The core is approximately 20 million degrees Celsius. And it's that high temperature and those large gravitational forces that are causing the nuclear reactions to occur. And so the answer to the problem or to the question has a name, of course. It's called hydrostatic equilibrium. But that's the fancy way of saying the outward radiative pressures and the inward gravitational pressures are balanced or equal. So the answer is called hydrostatic equilibrium, which I often will write like that. And of course, hydrostatic equilibrium is when the star's radiative pressure balances perfectly the star's gravitational pressure. Allowing our star to relatively keep its shape and remain doing what it's doing for billions of years. Okay, so we decided step 1 through 6 are the same, so we'll begin with step 7. Step 7. And so keep in mind, between step 6 and step 7, when the star is born and when step 7 begins, is 90% of our star's life. So this is what the slice of the inside of our sun probably looks like. And this is what our sun should look like for 90% of its life. When we get to step 7, we're really beginning to describe the death of a star. So we're now describing the final 5% of a star's life. So we'll say eventually, which is a big eventually, the hydrogen fuel begins to become exhausted. So I won't say so. Eventually, the hydrogen fuel begins to become exhausted. It's running out. At this point, the hydrostatic equilibrium is compromised, and the core begins to collapse again. Hydrostatic equilibrium is compromised, and the core begins to collapse again. In other words, the gravitational pressure, which doesn't change, starts to win over the radiative pressure that's diminishing as the hydrogen begins to diminish in the core. We want to note, meanwhile, the outer layers of the star cool off and expand. 1T. The outer layers cool off and expand, so it becomes a red giant. When our sun starts to go through this, when our sun becomes a red giant, we think some of the outer layers of the sun will reach to or almost to the surface of Earth. So this could make Earth life a little more uncomfortable. Okay, step 8. Now that we have our red giant, when the temperatures and pressures in the core again reach critical, so we'll say when the temperatures and pressures in the core reach critical, and this would be due to the collapse we're talking about in step 7, due to step 7. The degenerate, I'm going to put degenerate in quotes, helium in the core ignites. In a catastrophic explosion known as a helium flash. I like to note that during the helium flash, the triple alpha process begins. We're going to call that tap. I'll often write tap like that for alpha. The triple alpha process begins. And I'm going to note C step 9. Even though there's some argument over how quickly this happens. And then I want to note the degenerate helium is the byproduct, or produced by, of the proton-proton chain. In other words, it's the non-fusing helium in the core. And it's not until this second collapse that temperatures and pressures are large enough to force this degenerate helium to begin to fuse together. That helium fusion is known as the triple alpha process, and I'm going to give it a whole step, even though this probably happens in a very short amount of time. So helium fusion via the triple alpha process is essentially, and keep in mind all these chemical equations are drastically simplified. Helium plus helium plus helium, so triple alpha. Alpha particles are the nuclei of helium atoms, and that should give us some carbon and some energy. And so if you look at the periodic table, you'll notice that helium plus helium plus helium gives you 6 protons, and it turns out number 6 on the periodic table is our friend carbon. And so we'll say this process continues converting carbon or helium into carbon. This process continues converting helium into carbon until, and we'll have another an actual helium flash now. So the helium flash occurs. This will be step 10. So this helium flash that we spoke of before was the degenerate helium in the core igniting. It takes a huge amount of energy to do so. And this final helium flash is when the helium that is converting into carbon starts to run low on fuel, and the triple alpha process slows and then finally stops. So I'll note that. So we'll say as the helium fuel runs low, the triple alpha process slows and eventually stops. The remaining entity, so this is what is left. So when the helium flash occurs, most of the rest of the outer layers of the star are shed away, blown into space, and the remaining entity is called a white dwarf. So I'm going to say the remaining entity is white hot, spherical, rotating extremely fast, and made of high-density carbon. This entity is known as a white dwarf. The white dwarf has no fusion taking place. Has no fusion taking place and no source of new energy. A typical white dwarf has the mass of our sun, but is approximately the size of the Earth. That's why I say high-density carbon. So it's believed that the white dwarf has a maximum mass of 1.44 solar masses. Is believed to be the maximum mass a white dwarf can attain or have And this is called the Chandrasekhar limit. In case you're wondering. I will note one more thing. Eventually, the white dwarf cools. Now, this could take millions or billions of years. Eventually, the white dwarf cools and becomes a brown dwarf. And finally, a black dwarf, when it's cooled enough to not give off any light. We believe this is the fate of our sun. And these dwarfs are considered high-density stellar remnants. Thanks for watching.